what we're looking at for section 2.5 are perpendicular lines. Now, perpendicular lines are defined as lines that intersect to form right angles. So when we draw two perpendicular lines, we would say that they intersect at exactly 90 degrees. Fairly simple definition. Anytime we intersect 90 degrees. Now, theorem 2.4 says if two lines are perpendicular, then they form congruent adjacent angles. What this is saying is that if I'm given that these two lines are perpendicular, then I know angle 1 is congruent to angle 2, and angle 2 is congruent to angle 3, and angle 3 is congruent to angle 4. Because we're intersecting to form right angles, we have 1, 2, 3, 4 right angles. So this kind of goes in with perpendicular lines. This here is the definition of perpendicular lines. All right, and the rest of these are theorems created directly from the definition. The second theorem is theorem 2.5, which says if two lines form congruent adjacent angles, then the lines are perpendicular. So now we have two lines. We're not sure if they're perpendicular, but we're told angle 1 and angle 2 are congruent. Well, if they're congruent, they have to add up to 180. So angle 1 and angle 2 have a sum of 180. Okay, their measures do. Which means if they're congruent, they each have to be 90 degrees. And then by definition, they're perpendicular lines. So this is another theorem right here. Theorem 2.6 says if the exterior sides of two adjacent acute angles are perpendicular, then the angles are complementary. So what it's saying is if I have two acute angles right here, and I'm told that these two lines are perpendicular, which means we have 90 degrees here, then angle 1 and angle 2 are complementary. It's really only a two or three step proof here, just because any two angles that add up to 90 degrees are complementary. And angle addition says that this angle plus this angle equals this angle, which happens to be 90. So these are complementary angles. All right. Now, the symbol for perpendicular is this symbol right here. So if we want to state that two lines are perpendicular, I could say line AB, or segment, I'll say segment AB, is perpendicular to segment CD. You can do it just like that. For line XY, or segment XY, is perpendicular to segment PT, just like that. So that symbol will be used a lot in geometry. Here's some examples. If it says give the justification for the following statements, number one says if DB, now this should be ray DB, is perpendicular to, or segment DB, it doesn't really matter, is perpendicular to segment BF, then angle DBE is complementary to angle EBF. What says that if we have two perpendicular lines, we have complementary angles here? Well, you might remember we had theorem 2.6 that said if the exterior sides of two adjacent acute angles are perpendicular, then they're complementary. Well, that was our conclusion, was that they're complementary. So that was theorem 2.6. Now remember, we don't need to memorize these numbers necessarily. We could write out, and this is how I would abbreviate this, perpendicular segments yield complementary angles. However it is that your teacher would have you abbreviate that. And for number two, if angle EBC is a right angle, then EB is perpendicular to AC, which should be segment. Now, EBC is a right angle, then EB is perpendicular to AC. Where did I see right angles mentioned? Well, congruent adjacent angles, but no right angles mentioned here. No right angles mentioned here. But if you look at the beginning, oh, I see. The only one that really mentions right angles is right here. The definition. Remember, definitions are biconditional. So I can say perpendicular lines are perpendicular if and only if they intersect to form right angles. So the fact that I have right angles means I have perpendicular lines. So this is definition of perpendicular lines. If angle ABE is congruent to angle EBC, then EB, segment EB, is perpendicular to segment AC. So if I say this angle right here is congruent to this angle right here, then do I have two perpendicular lines? Well, let's see. We're looking for a theorem that said that we had congruent angles and that gave us perpendicular lines. Okay, let's see. Two lines, here we were given congruent adjacent angles and we concluded that lines were perpendicular. So that looks pretty good to me. So we're going to say it's theorem 2.5. If two lines form congruent adjacent angles, we get perpendicular lines. So this is theorem 2.5. And for me, I like to write out, all right, congruent adjacent angles yield perpendicular lines. Okay. And a couple of problems where it's solved here. It says, given BE is perpendicular to AC and DB is perpendicular to BF. This is perpendicular right here, and these are perpendicular right here. So perpendicular, perpendicular. It says if the measure of angle ABD is 4x minus 30, ABD, that's this angle right here, 4x minus 30, and DBE is x, how do we find x? Well, we say that those two should add up to 90 degrees. So we say 4x minus 30 plus x equals 90. Add those x's together. So add 30 to both sides. And we say, oh, that was super easy. And x is 24. The next one says angle DBE is 6x. We're just going to get these out of here now. And we say DBE is 6x. And EBF is 8x minus 2. And here we know that those two things should add up to 90 degrees. Oop. So I had a little bell go off there. Sorry, 6x plus 8x minus 2 equals 90 degrees. So we get here 14x equals 92. You say, oh boy, I got to calculate this. X is going to be equal to 6.5. I'm going to estimate here. It's approximately 6 and 57 hundredths. Okay, for x there. When we take 92 divided by 14. Okay, so that's how we solve problems like these. Thank you. That's the end.